So in yesterday's class, we've looked at the various aspects of uh, the integration windows and what ensemble averages are. In this lecture, we're going to look at correlations. So the moment of a random variable. So yesterday we had basically looked at the moments of a random variable, and the moment is surely interesting, but we are often more interested in the spatial extent of the fluctuations, that is how long they persist. So imagine a truly random noise. So truly random noise, the noise at the next time step will be ideally independent of whatever is going on. But oftentimes we see that many signals, large amplitude oscillations are accompanied with large amplitude oscillations, while small oscillations are accompanied with small oscillations. So this kind of behavior, you can say that it's intermittently becoming well behaved. So it is called as intermittency. So if you try to correlate what is happening after a small time, and you will see that a small value is correlated with another small value, a large value is correlated with another large value. So you are more bothered with the spatial extent or the temporal extent of the fluctuations. Okay. So in the study of turbulence, correlations and spectra, they're quite important because they help to characterize the fluctuations in a manner which is going beyond just moments. So what is actually a correlation? So the correlation Rij of something at x1 at time t1 with something at x2 at time t2 is defined as the ensemble mean of ui at x1 comma t and uj at x2 comma t. So this is defined as the correlation. So ui uj can be two. So ui and uj can be anything, but in the case of turbulence, this can be one velocity component. So it can be maybe the u component. This can be maybe the v component of velocity. And you're trying to, so x1 and x2 are different, and t1 and t2 are also different. So essentially, you're trying to ask the question: how correlated are u and v at locations x1, x2 with the offset t1 minus t2? Basically, if so, it is a measure of how similar ui and uj are. So a similarity index, if you like. This is not the accurate definition. It's more to understand what is going on. So Rij, that is the ensemble over all experiments of ui uj. If it is, you see that it is 0. So when can Rij be 0? When a positive value of ui is associated equally with a negative value of uj or a positive value of uj, and when a negative value of ui is associated equally likely with a negative value of uj or a positive value of uj. So uj is always evaluated at x2 t2. In the special case, x2 and t2 can be equal to x1 and t1, no matter. So x2 and t2, this is evaluated at, and this is evaluated at x1 and t1. So if this is true, Okay, if this is true, then you will have a negative product, positive product, negative product, all coming with equal probabilities from n different ensembles. So basically, if you recall, this particular term is essentially 1 by n, 1 by n, not a limit. This will be summation of ui, uj, and this is evaluated at x1 t1. This is evaluated at x2 t2, and over all the ensembles n equal to 1 to n. Okay, so because they're equally likely to yield a positive or a negative sign, you end up with a correlation which is close to zero. And this kind of situations, the variables, the variable pair ui and uj is said to be uncorrelated. Okay, they are said to be uncorrelated. Okay, now so the other case is when rij is a small value, then it is said to be weakly correlated. Okay, so if rij is small and positive, then it is said to be weakly correlated. If rij is small but negative, then it is said to be weakly uncorrelated. If rij is something very is positive, and when is rij going to be positive? First of all, when a positive value of ui is associated with a positive value of uj, and a negative value of ui is going to be associated with a negative value of uj, then rij will be positive. So this is called as a strongly correlated system. And lastly, when ui is related with a very correlated with a negative value of uj, and negative value of ui is correlated with a positive value of uj, then rij will be strongly negative, and this kind of a system is called as an anti-correlated system. So typically, rijs are normalized. So how do you normalize rij? So rij is by definition ui x1 t1 uj x2 t2, and you can normalize it, and you can say rij, and it is going to be, well, it is going to be rij upon square root of rii x1 t1 x2 t2 rjj x1 t1 x2 t2. So let us consider the example for 1 comma 2. So, or we can choose, let's say I equal to 1 and j equal to 1. In that case, we have r11 is equal to the ensemble average of u1 x1 t1 u1 x2 t2 divided by square root of u1 square mean x1 t1 times u1 square x2 t2 mean. Okay, and this is always bounded between 0 and 1, or rather not 0 and 1, but it is bounded between -1 and 1. So -1 will be anti-correlated, perfectly anti-correlated. And this will be perfectly correlated. Okay, and what assures you that this will be bounded between -1 and 1? There is a very famous theorem called as the Cauchy-Schwarz inequality. And that assures us that R12 will be bounded between -1 and 1. So with this in mind, let us proceed. Before we proceed, let me show you what actually a correlation looks like. Let us quickly define something. So Rij of tau. So correlations typically they depend on the offset, not the entire signal per se, and it is defined as Ui of t times Uj of t plus tau, and the mean of this. So if you have a signal something like this, and if you have another signal which looks something like this, then you have initially the same time offset. So tau equal to 0. So Rij for 0, you just multiply these two things and take a time average. You can do that, because in the last class we have seen that taking a time average is also tantamount to taking an ensemble average, and that is, I don't want to go into the details of it, but we've done this yesterday. So you multiply these two signals. So what do you see when you multiply these two signals? What do you see? You see that here, here, here. So they are sort of positively correlated. So Rij for 0, that will be something positive. Okay, like high value of this blue curve gives a high value of this green curve. High value of blue curve gives a high value of green curve. High value of blue gives high value of green. Here maybe not so much. Okay, so fine. So this is what you see. Then let us see what happens. Let us see what happens when you shift it. So when you choose a positive tau, uj at t plus tau, okay, it means that you multiply basically whatever is going on at time t, you multiply it with whatever is going on at t plus tau. So you have to shift this curve to the left. Alright. So this is that offset tau. So this offset is tau. So let us shift it by that offset and see what happens. There you go. So over here we see that low values of green are associated with high values of blue. Low values of blue are associated with middle values of green. High values of green, low values of blue. Low values of green, high values of. So at Rij at some tau, maybe say 5 seconds. So then it will become uh, either 0 or weakly positive. And weakly positive because of these regions. These regions will give weakly positive, but overall you see that once you shift over a certain time period, you no longer have that correlation. Okay, so this is what convolution means. You want to find out over what time period are these two curves going to be sort of similar in nature. So like this, they are good. Well, like this also they are quite similar, but once you shift it enough, there is no correlation. So for large taus, there is no correlation. So if I were to plot this, if I were to plot it as a function of tau, so for small values of tau, you have a good correlation. Then for large values of tau, we quickly see it becomes negative or weakly positive, so something like this. In fact, we can also do what is known as an autocorrelation. We can also perform what is known as an autocorrelation. Something like this. Mm, Ideally, I would have, yeah, something like this is fine. So, fine. So, when the shift is 0, they are perfectly correlated. Okay, when the tau shift is 0, then these two curves are perfectly correlated. R11 as a function of tau. So, when tau equal to 0, Rij will be 1. Now, when there is a slight increase in tau, so the pink curve will shift. There is still correlation. Now, there is still some correlation. Still some correlation. Everything is uncorrelated. When I shift a sufficient distance, or in this case, I mean, when I refer distance in this particular case, it is a time shift tau. Don't be confused by an actual physical distance. It is the time shift that we're talking about. So now there is absolutely no correlation. Okay. So after a large enough time, there is no correlation. So everything is uncorrelated. Okay. So it tells you that the curve will look something like this. So this particular time is sort of your characteristic time over which things remain correlated, or the velocity or whatever time signal you have remains correlated.